Welcome everybody to this class. My name is Caleb Curry and I'm the owner of this channel or website or whatever you're viewing this on. And basically in this video we'll be talking about binary. This is for pretty much absolute beginners. So if you don't know what binary is, that's okay. I'll be explaining that. And we will be going over the very basic concepts, but we will be getting into some advanced concepts, at least advanced for beginners. But I'll be trying to break it down very simple so we can go into that intermediate or advanced topic without confusing you. Alright, so binary. What is binary? Well, when we're working with computers, things are in two states, either on or off. So I guess you could say like a circuit is either on or off, or charged or not charged, and so forth. So we can get these bursts of on or off, and that's how a computer understands concepts. So it's kind of confusing at first, but we can illustrate or represent an on with a 1 or a 0 for an off. So binary is only two numbers, 1 or 0. So you could say it has a base of 2. So on or off, 1 or 0. So for the rest of this video, we will be using 1 and 0. This represents an on or an off. So you can kind of forget everything else. Just remember 1 or 0. Alright, so since it's a base of 2, what does that mean? Well, we can actually use binary to count. So just like we have a base 10 decimal system, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, this is 10 digits because we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total possibilities. Once we get to 9 and then we go one more, we get 1, 0. So we add an extra digit. Well, binary works in a similar fashion. So we could have 0, which is equal to 0 in decimal. So this is binary, this is decimal. We can also have 1, which is equal to 1 in decimal. Well, now we can't have 2 because if you remember, we only have two possibilities, 1 or 0. So what do we do now? Well, just like in decimal, when we get to 9, we add an extra digit. Same with binary. So we now have 1, 0. And we'll be explaining how to count this and so forth as this video goes on. So stick with it. So 1, 0 is equal to 2 in decimal. So over here's decimal. Over here's binary. So this looks like 10 to us, but computers understand this to be 2. So hopefully that makes sense. And then we can add another one and we get 1, 1. And this is equal to 3. So the counting system is different because we can't have a 2 or a 3 or a 4. That's what it means by base 2. There's two possibilities, 1 or 0. So if we were to add another one to this, we would end up getting 1, 0, 0, and then 1, 0, 1, and then 1, 1, 0, and so forth. And now we're going to be illustrating how you can count this, because if you think about it, when you have decimals, you have the first spot, so 0 through 9, and then once you go past 9, you add an extra digit, right? Well, so let's say we're at 9, and then we add 1 to it. We get 10. So you could say this spot right here is the ones place. This is in decimal, base 10. You could say this right here is the tens place. And then once we get to 99, and we add one more, we add another one, and you could say this is the 100s place. And then you could keep doing it. So if we're at 999, you add another one, you could say this is the thousandths place, and so forth. So when we're looking at a number, we can think of it like this. Let's say we have 6,000 in decimal, 6,343. Well, this is the thousandth place. Or we can go this way. Ones place, tens place, hundreds place, thousands place. So we have 3 ones, 4 tens, 3 100s, and 6 thousands. So when we read that the other way, 6,343. So you can think of this as 3 plus 40 plus 300 plus 6,000. And then we add this together and we get 3, 4, 3, 6, or 6,343. Well, the binary system can work in a similar way. But see, if you noticed, each extra digit in the decimals multiplies by 10. So we have the ones place, and then we have the tens place, and then the 100s place, and the 1000s place. It goes by 10 each time, times 10, times 10. This is because this is a base 10 system. What if we make this a base 2 system? Well, let's try it. Well, we can have the first digit, and a 0, correct? And we can also have a 1, correct? But we can't have a 2, so we have to add another place marker, and we get 1, 0. So we had 0, then we had 1, and then we had 2. So this is how you illustrate 2. If we keep doing it, so if we add 1, this is 3. Then if we add another one, well, we have to add another place marker because we can't have any extra numbers. Because we can only go to 1, we can't go to 2. So now we get this, 1, 0, 0. And this is equal to 4. So as you can see, when we have 1 place marker, and we can have up to 1, this is equal to 1. When we have 2 place markers, well, this can be equal to 2, because we get 1, 0. If we get 1, 0, 0, this is equal to 4. So as you can see, rather than multiplying by 10 each time, we multiply by 2. So if we have a binary number, such as 101101, you could say ones place, twos place, fours place, eights place, 16th place, 32nd place. So it multiplies by 2 each time rather than 10. So let me make that a little clearer because that was kind of smashed up. So if we have 1, 0, 1, 0. Well, this is the ones place. This is the twos place. 4, 8. So what number is this? Well, we have 2 and we have 8. So the answer is 10. Alright guys, so now you can see we have this binary number floating in the sky. Well, this is obviously equal to 0. It's the only number we have. Well, if we want to represent a 1, we can replace this 0 with a 1. Well now, since the only options we have are 1 and 0, we can't place a 2. The only thing we can do is move this to the next spot. So now, we have 2. You see? So we went from 1 being 1, and then to make it 2, we scoot it over and add a 0. So that's 2. Now if we want to represent 3, well, we add a 1. Well, this isn't a 1, so that means we can just replace it. This is 3. Well, now let's say we want to add another 1 to make it 4. Well, as you can see, we can't represent these as 2's because we can't use 2's. So the only thing we can do is add a 1 and replace them with 0's. So what number is this? First we had a 1, and then we had 1, 0, which is 2. Then we had 1, 1, which is 3. And then we had 1, 0, 0, which is 4. Okay, so now how do we represent 5? Well, 1, 0, 1. 6, well, we can't add a 1 here, so what we need to do is we need to move this up and replace that with a 1. So now we have 6. 7. And then if we want to add another one, well, we can't because we can't have a 2. So that means all of these become zeros. Let's get them up here. And we add a 1. So here we have 8. Now if we want to represent 9, add a 1. If we want to represent 10, well, we have to scoot this up 1 and add a 0. So this is 10. So here is what each spot represents. And we can keep multiplying this by 2 for as long as we wish, but this is as far as we are going to go. So if we have a 1 or a 0 here, it can only be a 1. So this means that's 0 because that's off. So we don't count 1. Then 1 is 1. Well, if we are looking at other numbers, let's say we have 1, 0, 1. Well, this is 1. This is 4. So the answer is 5. Here, I guess I can use some decimal numbers to represent this. So this is 5. Alright, so now what if we have 1, 1, 1? Well, this is 4, this is 2, and this is 1. So we get 4, 5, 6, 7. So this becomes 7. Alright, now I want to try adding 1 to this binary number. Well, we can't add it here, so that means we have to change something because there's nowhere to place this. We can only place it at the far right. So that means 4, 5, 6, 7. We can scoot these all up to 8 and add in the zeros. So that is how that works. We went from 3 1s, which added up to 7, to 1 1 that added up to 8. So if we were to go to 9, all we need is an 8 and a 1. If we were to go to 10, all we would need is an 8 and a 2. If we were to go to 11, we would need 8, 9, 10, 11. If we were to go to 12, we would need 8, 9, 10, 11, 12. So basically, we use these numbers to add together to give us the number we want. So right now we have 12. If we were to use 13, 13, 14, well, 14. There we go. Alright everybody, I hope that all made sense. I want to look at a few more things so that this will really click on our brain. This is another way to think of numbering systems. Let's first look at the decimal system. This is the one we are familiar with. It has a base of 10. This means there's a total of 10 digits, all the way up to 9. That includes 0. So 1 to 9 is 9 digits, 0 is the 10th digit. So it has a base of 10. Deci, that actually means 10. When we're talking about binary, well, bi actually means 2. So if we take a look at this base 10, and let's say we have a number such as 304. We're going to get into some math here, but don't freak out, nothing too crazy. You may have heard of something known as scientific notation. This is an easier way to write bigger or smaller numbers by simply saying what the number is and then multiplying it by 10 to the power of something, like 3 times 10 to the third. Now, how does this work? Well, 10 to the third is another way to write the place marker. So this is 10 to the 0th power. 10 to the 0th power, or anything to the 0th power, always equals 1. I don't know why it equals 1. I'm not very good with the whole mathematics crap, but basically anything to the power, anything besides 0 to the... Alright, let's say, yeah, 10 to the 0, that is 1. Alright, so we can assign this 10 to the 0, this 10 to the first, and this 10 to the second. So you can see it goes up 1 each time. So if you see 10 to the power of 1, that is the same thing as saying 10 times 1, which is equal to 10. Now 10 to the second power, that's like saying 10 times 10, which is equal to 100. If we had another one, it would be 10 to the third, which is like saying 10 times 10 times 10, or 1,000, and so forth. So if we had 10 to the 10th power, it would be 10 times 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 10. So we can view numbers that way. So we can figure out numbers. Let's say we have, let me get some more room up here. We have the number 304. And let's just work with this first spot right now. And that would be 10 to the 0th power, which, by the way, is equal to 1. How many of these do we have? Well, we actually have 4. So we actually multiply 4 times 10 to the 0th power. So 4 times 1 is equal to 1. So, because if you remember, a while ago in this video, I said this was the ones place, which is, another way to write that is 10 to the 0th power. So 4, oh, I'm sorry guys, that's not equal to 1. Sorry, I'm stupid. 4 times 10 to the 0th power, 4 times 1 is equal to 4. I probably just confused all of you after I said 1. But, so let me try a different number. Let's say this is 6. Well, we're in the ones place. That means we're multiplying by 1. Another way to write 1 is 10 to the 0th power. Why do we use 10 to the 0th power? It's a way to say that we are in base 10. If we write 10 to the 0th power, everybody's going to know that we are using base 10 system. So let's try 6. We have 6 to 10 to the 0th multiplied by 10 to the 0th power, which is 1. 6 times 10 to the 0th power, or 1, is equal to 6. So basically we have 6 in the ones spot, which obviously we do, because you can see it right there. Let's try the next one. Well, now we're not at 10 to the 0th anymore. We are at 10 to the first power. That's basically just saying 1 copy of 10. That's all it is. So now we have 0 times 10, which is equal to 0. Because if you multiply something by 0, you get 0. But if you're doing something to the exponent of 0, it equals 1. Just remember that. That's kind of confusing, but that's just something to do with math. So 0 times 10 is equal to 0. Or 0 times 10 to the first power, which is basically the same thing as 10, is equal to 0. Same thing. Alright, let's try the next one. Well, now we are on to 10 to the second power, or 10 times 10. Basically 2 copies of 10. 10 times 10 is equal to 100. So we have 3 instances or copies of 10 to the second power. What does that come out to? Well, 10 to the second power, that's equal to 100. 3 times 100 is equal to 300. So now let's put all of this together. we have 6, which is 10 to the 0. We have the 0, which is 10 to the 1. And have the 3, which is 10 to the 2nd. That's the place. So ones place, tens place, hundreds place. Alright, so now this is what we have. And then we multiply this by how many we have in each group. So we have 6 for the ones place, 0 for the tens place, and 3 for the hundreds place. So we get 6, because 6 times 10 to the 0. This is 1. 1 times 6 equals 6. This is multiplying by 0, so it's automatically 0. 3 times 10 to the 2nd power. Well, this right here is equal to 100. 3 times 100 is 300. So we get 300 plus 0 plus 6, which comes out to be 306. That is how this system works. Now we can try to do this with binary, now that we really understand that. I'm going to get a drink first, though. So if you remember, when I was talking about the decimal system, we multiplied by 10 to the nth power. N just means whatever decimal location we're at. So if we're at the 100 spot, that would be 0, 1, 2. Because 0 is how we represent the 1, so 10 to the 0th is equal to 1. So it's always 1 less than how many locations we have jumped. So 0, 1, 2, not 3. So that is, we use the 10 because we are in base 10. So we go 10 to like the 3rd power, for example. Or we go 10 to the 2nd, or 10 to the 24th, or 10 to the 240th, whatever we want. Well, we're in base 10. That's why we have the 10. Now, the reason we use this system is so we can use different base systems. So now if we're in binary, that has a base of 2. So now we are going to be using 2 to the nth power. Alright, so let's give this a try. Let's start with 2. We just can define some values. 2 to the 0th power. 2 to the 0th is 1. So 2 to the 1st, that's equal to 2. 2 to the 2nd, that is equal to 4. Basically, this is saying, this is 1. The next one is saying 1 copy of 2. Next one is saying 2 copies of 2. I got 2 to the 3 is equal to 8, which is 3 copies of 2. We multiply these together. 2 times 2 is equal to 4. 4 times 2 is equal to 8. So that's how that works. So 2, 2, 2. And then 2 to the 4th is equal to 16, which is 2, 2, 2 times 2. 2 to the 5th is equal to 32, which is 2 times 2 times 2 times 2 times 2. And it can keep going on forever and ever and ever and ever and ever until we die. So I'm not going to keep going on because I think you get the process. So we can use this to calculate binary. Ow! Oh, I just hurt my wrist on this thing here. Alright, so let's say we have the number, or the binary number of 1, 1, 1, 0. I know ahead of time this is equal to 10, just so you guys know. But you can see how I figure it out. So this is going to be 2 to the 0th power. This is going to be 2 to the 1st power. This is going to be 2 to the 2nd power. This is going to be 2 to the 3rd power. How many of these do we have? 0. That means it's automatically 0. If it's 0, you don't even have to do the math, it's 0. So this one right here is equal to 0, so we drop down to 0. This one right here is 0, so we drop down to 0. Now all we have to worry about is 1 times 2 to the 1st power. So 2 to the 1st power, that's basically 1 copy of 2, so we get 2. 1 times 2 is 2. So keep these numbers separate. This isn't like a continuous number. So 2 to the third power, that'd be 2 times 2 times 2. Well, 2 times 2 is 4. 4 times 2. So then basically you do these two and you get 4. Then 4 times 2 is equal to 8. So now this is equal to 8. So we add these together. 8 plus 2 is equal to 10. So that is how that system works. Let's try a more difficult one. Let's go 1, 1, 1, 0, 0, 1. All right, well, automatically, we know we don't have to worry about those. 1, well, that's 1, that's easy. And then, so this is multiplying by 2 to the 0th power. This one's 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th. Okay, so we have to worry about 2 to the 3rd. Well, if you remember from the last example, that's 8. So we have 8. And 2 to the 4th is just twice that. So we have 16. 2 to the 5th is twice that, 32. So the decimal system multiplies by, the binary system multiplies by 2, where the decimal system multiplies by 10, because we're in base 10 versus base 2. So then all we have to do is add these numbers up. Alright, so we got 32, 16, 8, and 1. Well, 8 and 1, that's 9, so yeah, I'll leave that there so we don't screw it up. We have 9, then 6 plus 2, that's 8. 9 plus 8 is 17, so we get 17. 1 plus 3 is 4, plus 1 is 5, so 57. So this is the binary representation of 57. That is how we can work with exponent scientific notation. Alright, sweet. Alright, now that we know how to figure out binary, read it and use scientific notation, etc., all that other stuff, we can start learning some more things about it. Well, when we're talking about binary, there's something we need to worry about. The total amount of values we can use, so total, and then also the highest number. So let's, probably doesn't make any sense to you, so let me just give you an example. Let's say we have this. 1010. This is equal to 10. You could say this, each one of these numbers here, 1 second, boy, is known as a bit. So that is a very important word you need to know. I probably should have told you that at the beginning, but oh man, I just got marker all over my shirt. So these are each known as a bit. This is a bit, this is a bit, this is a bit, and this is a bit. So you could say we have 4 bits in this number, correct? Well, we don't usually call it a number. We would call it a 4-bit word. So any string of binary ones or zeros, we would call this a 1, 2, 3, 4, 5, 6, a 6-bit word. So the entire string of binary is known as a word, and I don't know why they decided to use the term word. So 1010 is equal to 10. Now we are using a 4-bit word. Well, what if I wanted to know the highest number I could use with a 4-bit word? Well, that means we would have all ones. That would give us the highest number, because then all of the values would pass through. So what does that mean? Well, it's the ones value. Here are the place values. So we get 1 plus 2 plus 4 plus 8. So that is 8 plus 4 is 12 plus 2 is 14 plus 1 is 15. So another way you could think of this, let's try another way to get this. Well, we could do the exponential notation, or the scientific notation, and we get 2 to the 0th power, 2 to the first power, 2 to the second power, and then 2 to the third power. Well, same thing applies. This would be 1, this would be 2, this would be 4, and this would be 8. We add them together and we still get 15. That's just showing you both ways. Alright, so now I want to show you, this you could say is the highest number we could get. But how many values can we use? Well, that's actually 2 to the 4th power. So 2 times 2 times 2 times 2. 2 times 2, that's equal to 4. 4 times 2, that's equal to 8. 8 times 2, that's equal to 16. So we have a total of 16 values because we are have a 4-bit word. So we can figure out the total amount of values by 2 to the bit word. So what is it? Why are these numbers different? We did the math and it showed the highest number was 16, but if we do this way, by using the bit word length, it says 16. Well, 0 counts as one of the values we can use. So you could say 0 is the first value we can use, 1 is the second, 2 is the third, and then 15th would actually be the 16th value. So that gives us the total 16 values. So when you're working with binary and you're confused, you may be confused by one bit or one number less than you expected, rather than 255 you may get 256. Well, this would be the total value. This would be the highest number. I just wanted to make that differentiation so people don't get confused. So when we're working with this system, a bit is a very small amount of data. It's just a 1 or a 0. We actually have to use multiple 1s or multiple 0s just to create larger numbers or data. So a bit is very small. So we create some other bit with prefixes to allow us to represent more data. So you may have heard of like a kilometer, for example, which is 1,000 meters. Well, we also have systems like that for binary. So I'm gonna go, yeah, let's use red. I like red. So if we have 8 bits, no, I can't really see the red very well. Let's just use blue. 8 bits is said to be a octet or a byte. So a byte, I keep getting hurt. A byte is equal to 8 bits. Well, in binary we always work with doubles, so multiples of 2. 2, 4, 8, 16, 32, and so forth. So we can't represent 1,000 as in a kilometer is 1,000 meters. We can't represent that in a multiple of 2. So we use 1,024. So the way we get this is by using 2 to the 10th power, which is basically 2 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, times 2 times 2 times 2 times 2, and then times 2. So we get 4, 8, 8, 16, 32, 64, 128, 256, 512, and 1,024. So we can represent 1,024 bytes as a kilobyte. The same thing applies, 1,024 kilobytes as a megabyte. 1,024 megabytes as a gigabyte. 1,024 gigabytes as a terabyte. And then I think it's like petabyte or I don't know. Petabyte and then something else, I don't know. But that is a system. So when you say you have a like a 750 gigabyte processor, hard drive, well, that is a crap ton of bits that it's able to store within the system. So gigabytes, if you want to use easy math, I guess you could say a gigabyte is a 1,000 megabytes just for simple math, and then 1,000 kilobytes, 1,000 bytes times 1,000 bits. So yeah. Alright everybody, I know you're all probably thinking that binary is pretty awesome, but I just wanted to talk about a few more things to help familiarize ourselves with it even more. So basically now, when we use binary, obviously the more place values we have, the more values we can hold. So if we have two values, well, we can only represent 0, 0, 0, 0, 1, 1, 0, and 1, 1. That's not very many values, but if we add more place markers, we can have more unique values. So, in computer programming, or whatever, or pretty much anything dealing with computers, when we need more possible values, we're going to have a larger bit word, which if you remember what that means, that's just how many locations we have. So that would be 1, 2, 3, 4, 5, 6, a 6 bit word length. So we'll have a larger bit word if we need to represent a larger amount of data. Now something important to realize with binary is it's not only used to store numbers. So with binary, let's say if we're not storing numbers and instead we are storing sounds to create audio files, we're going to need a ton of different sounds. Like let's say we just had two sounds, 1 or 0. Well, that's not enough to create a song because there's multiple different pitches and volumes and so forth. So the larger the bit word, the more possible sounds we could have, the more accurate things could be to what a real live instrument would sound like, for example. So that's just an example with audio recording. So basically, the higher the bit word, the either more variety of samples we could have for or larger values in numbers. But there's a downside. It takes more storage and longer time to process, for example. So most of the time we will see 8-bit words, 16-bit words, and 32-bit words, and 64-bit words, and obviously you could still have like in between, you could still use like a 9-bit word, for example, but this is what you'll most commonly see. So to figure out the amount of possible different values you can assign a bit word, you use 2 to the power of whatever bit word length you want to figure out. So I want to figure out 8, so 2 to the 8th power, that would give me 256. This is basically saying 2 times 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 2. And each time you get a new value, keep multiplying it until you do it 8 times, or 2 times 8 copies of 2 multiplied by. You get the point. 256 values. If we are storing numbers, one of these values is going to be, so this is equal to 0. So if we're storing numbers in binary, the highest number we could use is 255. Although binary can be used for other things, like I said, sound samples. When you recreate audio files, it takes samples of real audio, like thousands of times a second, and then it puts that into binary, and then plays it back really fast, and it sounds like sound. I mean, it sounds like what it sounds like in real life. Well, if we only have 256 different values, it would sound bad, versus like if we had 100,000 different sounds, well then that's going to sound better. So what I just want you to realize is we are limited to a different amount of values based on the bit word length. Alright, so now I want to explain something you will probably run into when we're working with numbers in binary. Let's say we have a 3-bit word. That means there's 3 spots that we can have either 1 or a 0. Well, let's write out every single possibility. We could have 0, 0, 0, 0, 0, 1. I'm just going to represent it with a line, it's easier. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So here's all of our different possibilities. 0, 1, 2, 3, 4, 5, 6, 7. Up to 7 with 8 different possibilities. So this is a 3-bit number. Now I want you to look at this. When you're working with numbers, you may run into something known as a sign. And we often use this to represent negative numbers in binary. So, yeah, you may have wondered that. How do you represent negative numbers? Well, we use the sign, and it's the first bit within a bit word. So we could assign this first bit a new, we're not going to use it to calculate numbers anymore. We're going to use it to calculate whether it's positive or negative. So we could say all of the zeros, we could say they are positive, and if it has a 1, then it's negative. So now, since the first digit is taken up with this sign bit, well, that only leaves us with two spots to get a number. So before, we could go from 0 to 7, which gave us 8 values. Well now, since we only have 2 values, the only possible values are 0, 1, 2, 3. A total of 4 values. So if we want to represent positive and negative numbers, the amount of values we can use is cut in half. So as you can see, before we went all the way up to 7, but now this is represented as positive 0, positive 1, positive 2, positive 3. And this is weird, but negative 0, we'll get into that in a second. Negative 1, negative 2, and negative 3. So we can represent a total of 8 values, but the highest number is now cut in half because we have to represent the negatives and the positive numbers. Obviously there's a problem here because we have a negative 0 and a positive 0. So more complex systems are used to figure out how binary is calculated, such as 2's complement. So you might want to look that up. I'm not going to get into that right now. I just wanted to teach you that in mathematics of binary, we will have signed data types and unsigned. So if it's signed, that means it has that sign on there, which is why it's signed, which means the amount of values we have to represent negative and positive. So before we may have been able to represent up to 255 values. Well, now it's only going to be up to like 127, I think. But we can also display negative numbers. Unsigned does not have that first sign, and it's automatically assumed just to be positive numbers. So we would go back up to the highest number being 255. Well, how does the computer, or whatever you're working with, understand if it's signed or unsigned? Well, that is something you, as the programmer or software developer, would tell it. So I could say, if I'm, like, let's say I'm programming a database, I could say it is an unsigned integer, and so forth. And then when MySQL or whatever databasing program you're working with gets that number, it's going to know that it's unsigned, and it doesn't have to worry about negative, positive values. So that's 2 terms you are going to need to know when working with binary. When it comes to binary, there's another very important thing we need to talk about, and that is what's known as overflow. And this marker is not working out so well, so I shall get a new one. Overflow. So what is this? Well, basically, when we are limited, for example, we may be storing a data type of 4 bits. So that means we have 4 place values that we can put either a 1 or 0 in. That means if we store, let's say 1, just 1, it will probably be stored as this. So it still takes up 4 bits. I mean, if the data type can adjust for different lengths, then it will probably store it as this. But in some cases, it will be stored as this. So it just depends. But what if we put something in like 100 in here? Well, then it's going to cut it short to 4 bits and we're not going to get the proper value. So that's not going to work out so well. Alright, so overflow is a system. What if we have this 4-bit value and we have 1111? Yeah, I was right. And then we want to add 1 to it. Well, what do we do? Because normally we would just put a 1 here and we would turn these all into zeros, correct? But if we are specifically limiting this to a like 4-bit word, this isn't going to work because this is a 5-bit word. So what happens? Well, there's 2 main types of overflow I'm going to be talking about in this little part of this video series. So in overflow, numbers either saturate or they wrap. So what is the difference? Well, if numbers saturate, that means once you're at the maximum possible value and you try to add 1 more, it's not going to work and it's going to stay at the maximum possible value. So this doesn't have to be for binary, this can be for anything. So let's say we are, I don't know, let's just say we have a maximum value of 1025 for some reason. And we have 1025. So let's say we're just withdrawing money from the bank, and this is the maximum amount of money we're allowed to withdraw at one time for some reason, I don't know. And we try to withdraw $1 extra, 1,026. Well, it's not going to work, and it's going to stay at 1,025. It may even throw up an error or prevent the program from continuing. You never know. Well, that's saturate. We also have wrap, which wrap, that is going to, if you're at the maximum possible number, you go 1 extra, it's going to take us to our lowest possible number. So sort of like in a car, the amount of miles you have traveled, once it, in like old fashioned, I mean now it's digital, but the little rolling dials, once they reach 99999, maximum possible value, you add 1 more, and it goes to 00000. So that is an example of wrap. And as well, if you are using signed integers, for example, or numbers or whatever, and you add 1 to the maximum possible value, it may go to the lowest possible negative value. So for some reason, if you are at, like, if let's say the highest value you can have is 255, not 5, and you're adding 255 and 10, you may get something like negative 240 something or something like that, and that's going to throw off your program and not give you the proper results. So in your work, you have to worry about wrapping, the binary numbers wrapping, so that's something you have to worry about. You also have to worry about putting values in that are too large for the limited. So if we have 4-bit word, obviously we're not going to be able to store the number 6,352 in decimal, like the equivalent value of that in binary. So that's also something you have to worry about. Alright, so we have covered a lot of material over binary. And I mean, I could, like, this video could be forever long, but this is pretty much all I'm going to cover. Now I'm going to do a quick review and tie everything together. So with numbers, we have a base system. So for example, decimal means it is a base 10. Deci is 10. Well, binary is a base 2. You may hear this, you may hear the term radix, or the base of the number, or the, yeah. So you have to worry about the base, which is the total amount of digits you can use. So for decimal, you can use 0 through 9, 10 possible digits. But for binary, by the way, there's also like hexadecimal and octal and so forth like that, which we might be getting into those into a future video. But for binary, you only have 2 digits, on or off. And to create multiple we can use these to represent different things, and to create multiple possible values, we have to add multiple what's the term? So we could have like 1, 1, 0, 1 different place values, that's the word I was looking for, to represent more unique values. Obviously, the larger we get, the more unique values we can use. So when we're working with binary, you would say this is the 1's place, this is the 2's place, this is the 4's place, this is the 8's place, this is the 16th place, and it keeps multiplying by 2 each time. So if you have 1, 0, 1, 1, 1, well, that's basically saying you have 16 plus 8 plus 4 plus 0 plus 1, which gets whatever. I don't feel like doing math right now. You can also represent this with scientific notation. So the 1's place would now be the equivalent of 2 to the 0th power, which is equal to 1. And 2 to the 1st power, and so forth. And then you can multiply the value you have by 2 to the 2nd or 2 to the 3rd to get that value for the specific column in the place value. So when we're working with bit numbers, we have maximum value and the total possible amount of values. So for example, if we're in a 4-bit word, let's go 3-bit, it's easier. We could have, no, let's go 2-bit. We could have 0, 0, 0, 1, 1, 0, 1, 1. There's a total possibility of 4 possible bits. You can figure this out because we are in 2-bit words, so we multiply 2 to the 2nd power, and that comes out as 4. So we have 4 possible values. Well, the highest number here, this is 0, this is 1, this is 2, and this is 3. The highest possible value is 3, because we have to include 0 within the total possible values. Another thing we must worry about, oh, and by the way, you can continue to do that to figure out other possible values. So 2 to the 8th is going to come out as 256, and so forth. And you can just figure out, if you have an 8-bit word, what's the maximum total values. You use 2 to the 8th. If you want to know the highest number or the highest value, you use 2 to the 8th minus 1. That's because this includes the 0, so we subtract that from the total possible values to get the highest possible value. Another thing you must worry about is with signed and unsigned values. So signed can be negative or positive. Close enough. And unsigned is just positive. Why is it named this? Well, this has to do with a sign we attach on the farthest left. Well, it can be anything really, but for this example, it's going to be the farthest left placeholder. So if we are in 3-bit words, and we give all the values, we can get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. If we're using unsigned, this will give us 0, 1, 2, 3, 4, 5, 6, 7. If we're using signed, we take this first value, which tells us if it's positive. We can use a different value if we wanted, but for this example, it's going to be easiest on the farthest left. If we can say if this is negative. Also for this example, I'm making 0s positive and the 1's negative, but that is subject to change for specific applications if necessary. But for this plus is 0, well now we get 0, 1, 2, 3, and then we get negative 0, which that's obviously a problem. You're going to need a more complex system, such as 2's complement, which I'm not getting into that in this video, too complex, to make this video way too long. This would be -1, -2, and -3. So that is a signed value. Unsigned value would make them all positive. Now the next thing we learned about was integer overflow, or just binary overflow, whatever, it doesn't really matter. We had saturate, and we had wrap. Saturate keeps it if you're at the maximum possible value and you want to add one more. Saturate keeps it at the maximum possible value and it's either going to throw an error or not do anything or prevent your program from continuing running. Wrap rate. Why did I write rate? Wrap is going to bring it back to the lowest possible value, whether negative or whether it's assigned or unsigned values. There's a couple things I also did not get into in this series, which I might make another video sometime in the future, but I just didn't want to make this video forever long. With that, we really didn't, in binary, like I said, we can also use binary to represent sounds and so forth. So binary is not just numbers. We can use these combinations of numbers to represent different things. For example, the letter A. Well, how can we represent that if a computer only understands numbers? Well, we can represent that with a combination of binary. It can be anything. For example, I could sign 1110. I can make that A. This is something that can be done by the programmer, and then, very low level binary. You can just make this A, and this may be, you may hear this as a character set. For example, if some of you, we have like UTF-8 and so forth, you may have heard of ASCII, ASCII. This is some of the most common letters on the American keyboard that are represented in binary. So like 0, 1, 1, just whatever. I mean, I don't know. And I might do that in another future video. But we can represent numbers using binary as well. That is something you need to realize. So, for this specific video, we were using binary for numbers and pretty much numbers only. But for other applications, binary numbers can represent samples of an audio file, pictures, video, like pretty much anything digital can be represented by binary. Just remember, binary is only on or off. So it's really not numbers at all, it's just on or off. We're just using binary to represent numbers. Alright, we also didn't talk about adding or multiplying or dividing or pretty much any mathematics with binary besides adding 1. But I might do that in a future video. I don't want to get into this video. And what else didn't I cover? We didn't talk about decimals in binary. That's something you might also want to study up on. So I'm pretty sure that's all I really have to say about binary. Be sure to check out my website, calebcurry.com. Be sure to subscribe to me here on YouTube. That would greatly be appreciated. Like this video and leave me a comment if you have any feedback, corrections if I made a mistake, and also any suggestions or anything you liked about this video and how I can improve my presentation. That would be most useful. Thank you, and subscribe.